we're going to look at linear inequalities and their solutions. So let's get started. We're going to start by looking at two-variable linear inequalities. So let's see what this name means. So two variables. Well, that means our inequality has two variables. So if you notice in this first inequality, we have the variable x and the variable y. Now in this second one, we have an a on the left side of the inequality and another a on the right side, along with a b. Now this inequality still only has two variables, the variable a and the variable b. Now let's look at linear. So linear inequalities, well, both the variables are going to be raised to the first power. So for this first inequality, we have x raised to the first power and y raised to the first power. Typically when something is raised to the first power, we do not show this exponent. And then same for this second inequality. Both of the a variables are raised to the first power, as is the b variable. We saw the same thing when we were looking at two-variable linear equations. With an equation, the expression on the left, it's equal to, it's the same value as the expression on the right side. So for this second equation, what we're saying is that 4a minus 3 has the same value as 2a plus 3b. Now with inequalities, one side of the inequality will have a bigger value than the other side. In this case, 4a minus 3 is bigger than 2a plus 3b. But we may also have equality, as we do with this first inequality with the less than or equal to sign. What that means is the left side of the inequality, so 3x minus y, is either less than or equal to the right side, in this case 2. Let's do a quick review of solutions to linear equations. So which of the ordered pairs, x, y, below is a solution to the linear equation? So we have the equation y equal to 2/3 x plus 2. And to test to see which one of these is a solution, we're going to plug each of these ordered pairs back into the equation and see which one gives a true statement. So for this first one, where there is an x, we'll replace it with a 3, and where there is a y, we'll replace it with a 4. So we have 4 equal to 2/3 times 3 plus 2. So this is 4 equal to, these 3's cancel out, we have 2 plus 2. So this is 4 equal to 4, and that's a true statement. 4 is equal to 4. Let's try the second one. Again, where there's an x, we'll replace it with a negative 3. Where there's a y, we'll replace it with a negative 1. So negative 1 is equal to 2/3 times negative 3 plus 2. So we have negative 1 equal to, this is negative 2 plus 2. Negative 1 equal to 0. That's false. That's not a true statement. Negative 1 is not equal to 0. And then for the last one, again, where there's an x, we'll plug in a 0. Where there's a y, we'll plug in a 3. So we have 3 equal to 2/3 times 0 plus 2. 3 is equal to 0 plus 2. 3 equal to 2. That's another false statement. So the answer is the ordered pair 3, 4. Now what does this mean graphically? So here's a graph of our line. Has a y-intercept of 2 and a slope of 2/3. So the answer, 3/4, that solution, is on the line. But negative 3, negative 1, that ordered pair is not on the line, nor is 0, 3. So the solution set for a linear equation, well, that's a line. And so the set's going to include all those points that are on this line, these infinite number of ordered pairs that make up this line. And yes, I did say infinite. There will be an infinite number of points on that line. So an infinite number of solutions. Now let's switch to linear inequalities. And we're going to define which of the ordered pairs below is a solution to the linear inequality. So this is similar to our equation we just looked at, but instead of having an equation, we have an inequality. But we're going to start the same way. To see if it's a solution, wherever there's an x, we're going to plug in this 3. Wherever there's a y, we're going to plug in a 4. And see if we get a true statement. So we have 4 less than or equal to 2/3 times 3 plus 2. So 4 less than or equal to 2 plus 2. So we have 4 less than or equal to 4. That's a true statement. For this next ordered pair, where there's an x, we'll plug in a -3. Where there's a y, we'll plug in a -1. So we have -1 less than or equal to 2/3 times -3 plus 2. So this is -1 less than or equal to -2 plus 2. So now we have -1 less than or equal to 0. Is -1 less than or equal to 0? Yes, -1 is less than 0. So this is also a true statement. And then finally, where there's an x, we'll plug in a 0. And where there's a y, we'll plug in a 3. So this is 3 less than or equal to 2/3 times 0 plus 2. So 3 less than or equal to 0 plus 2. 3 less than or equal to 2. And 3 is not less than or equal to 2, so this is a false statement. So the answer here is the ordered pair 3, 4, and the ordered pair -3, -1. Well, let's take a look at this graphically. Now we haven't discussed graphing inequalities yet, and we'll be doing that in a future lesson. But here we have the graph of our line, y equal to 2/3 x plus 2, and then one side of the graph is shaded. Now the ordered pair 3, 4, well, that's on the line. -3, -1, that's within our shaded region, and 0, 3 is outside the shaded region. So the solution set for a linear inequality, well, that's going to be a region on the graph with a boundary line. So here we have our boundary line. This is that y equal to 2/3 x plus 2. And then a region is shaded. And all the ordered pairs in this shaded region are a solution to this linear inequality. So again, we have an infinite number of ordered pairs that are a solution to this linear inequality. Not all ordered pairs. There's an infinite number of ordered pairs in this unshaded region that are not a solution, including the ordered pair 0, 3. But there's an infinite number of ordered pairs that are. And again, our solution set is a region on the graph. So which of the ordered pairs below is a solution to the linear inequality? And we have y greater than 1/2 x minus 3. And we have 3 ordered pairs. So we're going to test all 3 of these to see which one, if any, is a solution. So for the first one, where there is an x, we'll plug in a -4. Where there's a y, we'll plug in a 2. So we have 2 greater than 1/2 times -4 minus 3. 2 greater than -2 minus 3. 2 greater than -5. That's a true statement. So this is a multiple choice question. So let's see if we can eliminate some of our options. So -4, 2 is a solution. So let's put a check mark by that. So negative 4, 2 is also present in this choice. I'm going to put a little check mark by those values. Now we do have at least one solution, so none are solutions. Is not a viable answer anymore. And then we also have this option here that says only 2, negative 2, and 3, negative 4 are solutions. Well, negative 4, 2 is a solution. So we can eliminate this choice, this option as well. So we've gone from 8 options to 6 options. And we've done this by only checking one solution. So let's check the second one. So wherever there's an x, we'll plug in a 2. And wherever there's a y, we'll plug in a negative 2. So negative 2 greater than 1/2 times 2 minus 3. This is negative 2 greater than 1 minus 3. This is negative 2 greater than negative 2. So here we found equality. The left side and the right side are equal to each other at this ordered pair. But equality is not an option here. We have y greater than, not y greater than or equal to. So this is false. With this being false, we can exclude that answer and anything that includes that answer. So we can eliminate that choice. We've eliminated one of the solutions, so all 3 are solutions is also not a valid answer anymore. This leaves us with 3 options. So we need to find if 3, negative 4 is also a solution. So wherever there's an x, we'll plug in a 3. Wherever there's a y, we'll plug in a negative 4. So we have negative 4 greater than 1/2 times 3 minus 3. This is negative 4 greater than 3/2 minus 3. We're subtracting fractions, so let's get a common denominator. Negative 4 greater than 3/2 minus 6/2. Negative 4 greater than negative 3/2. Let's convert this fraction to a decimal. Sometimes it's easier to compare as a decimal. So we have negative 4 greater than negative 1.5. Negative 4 is not greater than negative 1.5, so this is also false. So we've eliminated 3, negative 4 as an option, as well as any choices that have that value. And so we're left with one ordered pair. So the ordered pair negative 4, 2 is the only ordered pair of the 3 given that is a solution to this linear inequality. Looking at a graph, and again, we don't need to graph in order to answer this problem, but sometimes it helps to visualize what is happening. So here's our line, y equal to 1/2 x minus 3. Negative 4, 2. This point is in the shaded region that represents the solution set for this inequality. So 2, negative 2, that's on the boundary line, and the boundary line is not a part of this solution. And then 3, negative 4 is outside the shaded region and is not a solution. A great way to learn is to practice on your own. We will discuss in a bit, but go ahead and pause your screen and do these 2 problems. So the first problem, we have which of the ordered pairs below is a solution to the linear inequality. We have y less than or equal to negative 2x plus 1. We're going to plug each of these 3 ordered pairs into the inequality and see if we get a true statement. So with the ordered pair 2, 4, we plug this in. We end up with 4 less than or equal to negative 3. That's false. So we can eliminate that option, as well as any of the options that contained that ordered pair. And also, all 3 are solutions is no longer an option either. So we've gone from 8 choices down to 4. Looking at the second ordered pair, plugging that in, we end up with 3 less than or equal to 3. 3 is equal to 3, so that's a true statement. So this is a good choice still. We have a solution, so we can eliminate none are solutions as an option. So now let's test this third ordered pair. We substitute in those values, and we end up with 1 less than or equal to 5. And that's also a true statement. So -2, 1 is a solution to this linear inequality. These are both solutions, so only -1, 3 and -2, 1 is the correct answer to this problem. So we have a little different approach on this practice problem. So we're going to write 2 solutions to the inequality below, and then write 1 ordered pair that is not a solution to the inequality. So you have to come up with some ordered pairs. But we have a lot of choices to choose from. There's an infinite number of solutions to the inequality. There's also an infinite number of ordered pairs that are not a solution. So let's see how to approach a problem like this. I'm going to select the value for x. And I will typically pick the number 0 because it makes the arithmetic easier sometimes. Now I'm going to plug that value in. So we have y greater than 0 plus 1. So completing the arithmetic on the right side of this inequality, we have y greater than 1. So I can pick any value of y that is greater than 1. Well, let's go y equal to 2. So now we have the ordered pair 0, 2. And we can test that. So we have 2 greater than 0 plus 1. 2 greater than 1. That's true. So let's pick another value for x. I'll go ahead and pick x equal to, let's do -2. So now we have y greater than -2 plus 1. Y greater than -1. So now we can pick a y value greater than -1. How about 1? So we can say y is equal to 1. Now we have the ordered pair -2, 1. We can quickly check this. So we have a y value of 1 greater than -2 plus 1. This is 1 greater than -1. And that's a true statement. So 2 solutions are 0, 2 and -2, 1. So now let's look for something that is not a solution. But we're going to start the same way. Let's set x equal to 1. Again, you can pick any number for x that you'd like. So now we have y greater than 1 plus 1, or y greater than 2. Now, if we were trying to find a solution, we could pick a value greater than 2, like 3 or 5 or 1,000. But in this case, we want something that is not a solution. So we're going to go the opposite way. We're going to select a y value that is not greater than 2. In this example, you could pick 2, because 2 is not greater than 2. But how about we go with y equal to 1? So we have the ordered pair 1, 1. And if we plug this in, we get 1 greater than 1 plus 1. So 1 greater than 2. That's a false statement. And that's what we expect for an ordered pair that is not a solution to the inequality. So not a solution, we're going to use the ordered pair 1, 1. Again, these are just my examples. I'm not really a gambling person, but I'd probably bet a pretty big wager that you did not come up with these 3 choices. But what you're looking for, any ordered pair that's in this shaded region, but not on this line, would be a solution to this inequality. And then any ordered pair in this unshaded region would not be a solution. Drop any questions you have in the comments. Continue working with the solutions for linear inequalities, and I'll see you in the next video.